I did want to get a little bit into this paper. I think I can probably get through in 15 minutes. This is a recent paper in Artificial Life. This is thinking about embodied collective cognition systems. So again, these are like agents that are doing collective behaviors and they're embodied. And it's called System 0123. And some of the System 1, System 2 types of cognition that's in the cognitive science literature, you kind of know what this means. Let's go through. This is from a Japanese group, I think based at Kyoto University, University of Tokyo. And yeah, so they're kind of taking, again, like Sakana, they're taking a perspective that's a little bit different than the sort of the Silicon Valley slash MIT, Stanford school of thinking about this. So let's go through the abstract. So the article introduces the System 0123 framework as an extension of dual process theory, employing a quad process model of cognition. So dual process theory is where you have two types of thinking. So you have like the basic type of thinking, and then you have the reflective type of thinking. That sort of hierarchy. Ron Sun developed dual process theory for cognitive architectures. So this is also another place where this is coming from. So they're developing this system for different levels of thinking in an agent. So they're employing this quad process model of cognition, meaning there are 4 levels of thinking in terms of cognition. So expanding upon System 1, which is fast intuitive thinking, and System 2, which is slow deliberative thinking. So this is the System 1 and System 2 distinction made by Kahneman, where you have the system that allows you to make fast judgments, it's intuitive, and then you have the slower system, which is deliberate thinking or reflective thinking. But they're also building 2 more levels onto that. So the first additional level is where, like, it's a System 0, which represents precognitive embodied processes. So it's like what's happening with the body. We know that there's a lot happening in the sensors in the skin, sensors in the muscle, that gets processed up to the brain. That's all that sort of System 0. So you have to have a body. The body's taking information from different directions. It's being integrated in the peripheral nervous system before it goes to the central nervous system. So that's System 0. There's also, we know that there's this pre-filtering function within the peripheral nervous system. So not all information gets represented in System 1 even. It gets pre-filtered and gets presented to System 1 in a certain way that then System 1 can operate on. And then, of course, System 2 will take that information as well. So we have System 0, which is this embodied specific level. We have System 1, which is this fast intuitive thinking. And then System 2, which is slow deliberative thinking. And then System 3, which is, of course, encompasses collective intelligence and symbol emergence. So it's this level above deliberative thinking, reflective thinking, which is where agents are collectively doing things. So we've talked about, first of all, we've talked about the emergence of collective behaviors, which is not something that is, additive from individuals. It's more of something that emerges from their interactions, but also from this concept of stigmergy. We talked about this, I think, on Monday in the EVOR meeting, which is where you have this, where you might have environmental cues that get deposited by individuals. They could be maps, they could be signs, they could be pheromones that guide the rest of the people or the rest of the organisms in the collective to a certain outcome. So this is the Systems 3 thinking. Okay, so we have System 0, 1, 2, and 3. We contextualize this model with Bergson's philosophy by adopting multiscale time theory to unify the diverse temporal dynamics of cognition. System 0 emphasizes morphological computation and passive dynamics. illustrating how physical embodiment enables adaptive behavior without explicit neural processing. Systems 1 and 2 are explained from a constructive perspective, incorporating neurodynamical and artificial intelligence viewpoints. In System 3, we introduce collective predictive coding to explain how societal-level adaptation and symbolic emergence operate over extended timescales. This comprehensive framework ranges from rapid embodied reactions to slow-evolving collective intelligence. So this is not only a difference in sort of level of processing, but it's a temporal difference. So the lower levels are faster, they happen at a more rapid pace, and then the higher levels build upon that, and they can draw from a sort of a long series of events. So systems 0 and 1 have a long series of events that they're exposed to. Systems 2 and 3 can sample from that and produce an outcome. So systems 1 and 2 are explained, okay. In System 3, we introduce collective predictive coding to explain how societal level adaptation and symbol emergence operated over extended timescales. This comprehensive framework ranges from rapid embodied reactions to slow evolving collective intelligence, offering unified perspective on cognition across multiple timescales, levels of abstraction, and forms of human intelligence. The System 0, 1, 2, 3 model provides a novel theoretic foundation for understanding the interplay between adaptive and cognitive processes, thereby opening new avenues for research in cognitive science, AI, robotics, and collective intelligence. So this is, something that's kind of similar to what we're doing with metabrain models, and kind of similar to this notion of sort of continual learning, where you have this, we have this sort of learning as a time series, or learning from a time series, and then building upon those events. And sometimes that sequence is not linear. So, you have sort of exposure to an environment that's continuous, and some component of the agent is sampling from that, and then, acting upon that, but it's not necessarily linear. It's not necessarily completely sampled. And there's all sorts of interesting dynamics going on there. So I think this gives us a framework for thinking about sort of the hierarchy of processing, but also thinking about continual learning. So, they talk about System 1 and System 2. They cite Kahneman and Bengio, talk about this in human cognition and in AI, respectively. And so, they talk about the System 1 and System 2 models, which have sort of a limited application. So why do we want to add levels? And that's because the System 1, System 2 dichotomy focuses primarily on internal cognitive processes, overlooking embodiment and sensory motor interactions of the environment. They do not account for collective intelligence, in which language and symbol systems evolve dynamically within human societies. They lack a broader temporal hierarchy, failing to capture how cognitive processes unfold across multiple timescales, from rapid reflexive reactions to the slow evolution of societal knowledge. And so then these limitations become more pronounced as we try to interact more with the real world. So if we're building embodied AI systems, we see the problems with this simple dichotomy, and we need to add more levels to get this sort of a better integration with the world, better continual learning. So a lot of times robots fail to adapt to real-world behavior because their cognitive models often fail to integrate fast, reactive motor control with slow, deliberative planning. Moreover, AI and robotics face challenges in modifying the languages they use for communication and in contributing to the cultural and societal formation necessary for collective survival. Their cognitive models often fail to manage long-term collective semiotic dynamics, that is, symbol emergence, hindering their ability to flexibly adapt to language and symbolic systems in the context of their environment. So they talk about the System 0123 framework. This framework is inspired by Bergson's philosophy of time, which provides a theoretical foundation for understanding how cognition operates at multiple temporal scales, from super fast embodied reactions to super slow collective intelligence. So I like how they frame sort of the embodied reactions to collective intelligence in terms of time. I think that's good. Especially thinking about those time scales and the differences between them and how those interactions tend to happen. Then they bring up the free energy principle. So inside the brain, we have the free energy principle and how this gives us a model for how biological systems remain adaptive. However, cognition is not limited to processes within an individual brain. And so they have very heavy emphasis on semiotics here. So in semiotics, it is widely recognized that symbol systems have arbitrariness, meaning that the relationship between the signifier and the signified is not fixed and evolves across communities and time periods. We emphasize this arbitrariness to highlight the core argument of this article, the existence of super slow dynamics in human or collective intelligence. Human societies continually update shared symbol systems, that is, systems of signs and their relationship with phenomena over time through social interactions. This arbitrariness allows adaptive flexibility and semiotic communication. Humans utilize a semiotic plasticity, analogous to neuroplasticity in the brain but not identical to it, to engage in intelligent activities no single individual can achieve alone. And this is what they refer to as System 3. So yeah, then they kind of talk about how you have all sorts of different types of adaptive behaviors without neural learning. They bring up passive dynamic walkers as an example of this. These examples illustrate how body-environment interactions contribute to flexible, robust, and intelligent behavior generation. And then they kind of contrast what they're doing with foundation models and multimodal large language models. Robotics foundation models focus primarily on computational data processing and neglect embodied interactions. So this is why they're proposing this System 0123 model as sort of a robotics foundation model. And then they talk about richer hierarchical timescale or MTS understandings of cognitive systems. We aim to establish a reciprocal dialogue between Bergson's theories of memory, the emergence of consciousness, discussions of cognitive systems and intelligence. We attempt to extend Bergson's MTS framework, which is this richer hierarchical multi-timescale framework, by examining both its similarities and differences to contemporary cognitive models. So, and then of course their System 3 is rooted in the collective predictive coding hypothesis introduced by Taniguchi in 2024. And so that's how they developed their System 3, but they basically want to extend Systems 1/2 into this quad process model. Okay. Yeah, so that's basically the idea, and it really kind of goes over a lot of this and reviews it. Thinking about fast and slow and neurodynamical systems. So, again, we're dealing with fast systems 0 and 1, slower systems 2 and 3. And then, so their approaches were inspired by the dynamical systems theory for autonomous agent behavior, emphasizing the tight coupling between the agent's internal dynamics and the external dynamics of its environment. So this is where they quote Randall Beer, some of his earlier work from the 90s. This original dynamical systems approach, which may correspond to systems 0 and 1, explain an agent's lower level or reflexive behavior in response to environmental changes through the concept of entrainment into attractors. So they talk about this tight coupling, which is, of course, a closed loop feedback system, and that closed loop feedback system is tightly coupled. So if we think about like sensory motor embodiment, we can think about like the body as being tightly coupled to the environment relative to maybe like symbol production or reflexiveness in terms of like what am I thinking. And so this tight coupling has, it has a very strong connection with this shorter time scale. Because if you have a longer time scale, you have too many things that can intervene in that tight coupling, and that feedback loop, or the efficacy of that feedback loop breaks down. So we're all familiar with the sort of the tight sensory motor coupling that you see with, say, like an agent that's interacting with, say, its environment, where maybe it's trying to walk or it's trying to move an object, and it gets constant feedback from the environment, and it's basically trying to match what's in the environment. So that's system 0 and 1. And so it's very easy to model that. We know how to do that. But then we also have, of course, these levels 2 and 3, or these systems 2 and 3. So this is where we need to add in an internal model to this. So we have the internal dynamics and the external dynamics of the environment characterized by this tightly coupled closed-loop feedback system. But then we also have this internal model, which is where this is something as classic in robotics. This was developed first by Wolpert in 1995, where they have a forward model and they have a reverse model. So they have the forward model, which is sort of the predictive model, and the reverse model, which is sort of the model that produces the behavior. So they go back to Wolpert's work in 1995 on forward internal models, which correspond with the so-called world models used in recent model-based reinforcement learning frameworks. So we didn't, in our paper, and in fact in that whole special issue, they didn't talk anything about sort of internal models or forward and reverse models that they use in robotics. I don't agree that it's necessarily the same as what people are talking about now as world models. So we have the Hahn-Schmidt-Huber work and the Hafner work, which is, of course, where people are talking about world models. This is kind of an earlier iteration of this work. Basically, it's the idea that, if you have a robot that's doing some sort of sensory motor operation, that it's not just a tightly connected or a tightly integrated closed loop feedback. It's actually where you have resources, like symbolic resources, that you can draw from to generate behavior. So this is, a little bit more advanced or a little bit higher level than the closed loop feedback, but I wouldn't say that it's kind of the same thing as world models. It's very similar, but not really. But early work on robotic navigation problems demonstrated that the topological structure of the task space can be embedded as multiple attractors in an RNN by learning sensory motor experiences. So that's sort of the idea that you have this dynamical system where you have closed loop feedback as a very immediate thing, and then you have this dynamical system that unfolds that the agent has access to through these attractor basins. So it can interpret the outcomes of these dynamical systems interactions as these attractors. And so then they just talk about how continuous sensory motor experiences with minimal constraints can lead to higher order behaviors. Tani proposed hierarchical RNN models, such as RNNs with parametric bias and multiple timescale RNNs, to introduce a temporal hierarchy whereby the lower level exhibits a high temporal resolution, which may correspond to the system 1, and the higher levels exhibit a lower temporal resolution, which may correspond to a system 2. So this can all be fit into a model of neural dynamics, where different levels of different neural dynamics, and then we can map those two together. The mutual interaction between the top-down predictive and bottom-up recognition processes can be understood as the RNN implementation of predictive coding. And here they cite Rao and Ballard from 1999. So they have this predictive coding aspect to this. So I guess you're kind of matching the two different timescales through predictive coding. And so people have tried this with different things such as object manipulation, imitation, language acquisition, and social interaction. And so there's this RNNPB, which is, of course, this approach by Tani, which is the RNN with parametric bias. And then there's this MTRNN, which is the multiple timescale RNN. And there are differences here between these two types of models. RNNPB focuses on different frequencies of neural dynamics and its updates to the system, whereas the MTRNN incorporates multiple timescales by assigning different time constraints to each network level. At a higher level, larger time constants produce slower neural dynamics, whereas at a lower level, small time constants lead to faster dynamics. And so this is just kind of thinking about these different levels and how they contribute to sort of an integrated neural system that operates at different time scales that allow you to build these primitives, say in sensory motor control, that would be like a bring function, a grasp function, a reach function, and a release function. And then at the higher level, you're combining those into sequences of movements. And so that's how this works. You start with this sort of tightly controlled closed loop feedback. You build primitives from those, and then you combine those together. And they're all happening at different time scales.